So welcome, guys. This is the last presentation of the semester. So here we go. Our group is number 7, and we did drain times of a bucket, the hole size, and our controls was the amount of water and the size of the bucket.
So our null hypothesis was that increasing the size of the hole in the bottom of a bucket linearly will result in exponential decay for the amount of time it takes for the bucket to drain. This was due both to the fact that the flow rate equation has a square in it from the area of a circle, but also the fact that the water pressure above the hole decreases as time goes on, as the water flows out. And then alternatively, we said that this would result in linear decay as opposed to the exponential. Next slide, please. So to perform the experiment, a cylindrical 5-gallon bucket had 5 holes drilled in it, starting with 3/16 inches, then going up to 1/4 inch, and then going up by 1/4 inch until a full 1 inch. And then when the holes were not being used, they were covered with waterproof Gorilla Tape. Okay, so to perform the experiment, a gallon of water is measured for the 5-gallon bucket, which then was put into the bucket that had the holes in it, which was then tilted at an angle of 8.35 or 53 degrees, where it was then tested to drain. So the water level had to be checked every 2 trials. As there was some evaporation or loss of water due to splashing. So after 10 trials, the bucket was removed, holes would be changed, and then repeat the process just by measuring time.
So this is our data for the 5 different hole sizes. We did 10 trials, so then we have the averages. Same thing for the water. And for the air temperature, that is the average between the start temperature for the first trial and then the temperature at the end of the 10th trial for each. And this is just all the raw data. So you can go to the next slide.
So our goal was to create a nonlinear fit of the data with kind of using Bernoulli's fluid flow equation as a base for that. And we were able to do that. At first, we tried to fit our data to a 1/x nonlinear fit line, and that got pretty close, but it kind of strayed away from the larger hole sizes. So we decided to scrap that and re-experiment with a 1/x squared fit. And as you can see from the graph on the right side of the page, does fit the data pretty well. And this data is the average times for each hole size. We did 10 experiments per hole size. And as you can see, our standard deviation was pretty low compared to how large the numbers in seconds were. And we did get a linear fit with a 95% confidence that that coefficient is between 10.56 and 11.41. So the model we used was just a simple coefficient of A over x squared. That coefficient ended up being 10.99. And as you guys saw from the graph, it fit the data very closely, just except for those last 2 data points. And we figured out our error in that.
So our results led us to accept our null hypothesis that by increasing the size of the hole on the bottom of the bucket linearly, the time it takes for the bucket to drain will decrease exponentially. The equation we got to describe the relationship between the size of the hole and the drain time is the y equals 10.99 x power 2.
So some possible problems that may have arisen from our experiments and our testing is that when using the Bernoulli's equation, we made a lot of assumptions, such as assuming that atmospheric pressure was constant throughout the system, which may not have been entirely true. We also assumed that the velocity of the water leaving the bucket was constant, or at least leaving the bucket the moment it left the bucket. We also may have not totally accounted for a streamline problem where Bernoulli's equation is dependent upon. Some other problems that may have arisen also include when plugging up the holes of the bucket, we may have changed the internal volume, which may have displaced a little bit of the water. Also, when draining the water, we recycled that water, so evaporation may have occurred, and also maybe a little bit of spillage. Furthermore, maybe some smaller, minute human errors may have occurred during the experimentation, such as vibrations or any kind of like displacement of the bucket.
And some of the things we learned were that there are a lot more factors to control than we might have originally thought when we came up with the idea, including, as mentioned previously, the pressure change, the velocity change. The density might have been slightly different with different amounts of water. It's not going to be perfectly constant density throughout. And also it wasn't a linear velocity profile. So some of the things were kind of more estimations. Also, we had to use different communication methods like direct messaging and group chats, which meant that we had to wait between like possibly an entire day to agree as a group on changes. So that was also a problem that we had to figure out. And luckily for us, we had a lot more time available in our timeline for mistakes, so that we didn't get behind at all. Some of the things that we could have considered doing were using better measurement tools to be more precise with our measurements. Also using a robotic system potentially for doing the repeating trials or measuring the water every time between trials would have at least allowed for more predictable error ranges. Also, measuring more variables would have been an interesting change to our project. Using different fluids with different densities would have allowed us to track the densities even if they're not going to be a constant density throughout. Thank you.